respiration sensing from thermal imagery while exercising.
Hi everyone, I'm Rishiraj. Let me start with a question. How many of you here use smartwatches for fitness monitoring? Please raise your hands. Yeah, many. So when we look at smartwatches, we look at two important metrics, which is step count and heart rate. But besides using step count and heart rate, another important metric that we are always interested in is calorie burn, or how much calories we have burned, which is also known as energy expenditure. But you will be very surprised to know that the calorie burn estimate of smartwatches are wrong by about 40%. But why this is the case? Because smartwatches mainly rely on heart rate to estimate the calorie burn. But as you can see in the equation, energy expenditure is a function of not only heart rate but also oxygen. But the gold standard of measuring calorie burn is indirect calorimeter. What the indirect calorimeter does is not only senses heart rate but also senses that oxygen which is required for accurate estimation. So on one end, we have smartwatches which gives inaccurate energy expenditure estimation, and on the other end we have indirect calorimeter which is accurate. To this end, I introduced JoulesEye, which is a system of energy expenditure estimation via respiration sensing from thermal imagery. JoulesEye works by fixing a thermal camera into a smartphone or a smartwatch. So JoulesEye sits somewhere in between smartwatches and indirect calorimeter. It is more accurate than smartwatches, and it's more practical to use compared to an indirect calorimeter, which is difficult to use and cannot be carried around. So the way the system works is from the thermal image that is captured by the smartphone or the smartwatch, we extract out respiration rate from the thermal imagery, and that respiration rate is modeled to estimate accurate energy expenditure. Now let us look at how respiration rate is sensed using thermal sensing. So if you look at the nostril, or when we breathe in and breathe out, our air is usually the area that we are exhaling is hot. So that hot air is clearly visible in the thermal imagery, and we can use this information for modeling the energy expenditure. But this is not very simple when it comes to when a person is doing some kind of activities. For example, in this image, in this GIF, the person is running by keeping his smartphone in the handrail or in the next of the treadmill, and the person is running. While the person is running, there's a lot of movement happening, which is vigorous movement. It becomes very difficult to track the nostril. So one idea is to use some facial landmark detection models which are exclusively trained on thermal imagery. But when we applied such an algorithm or such a model to our data set, we found out that initially it works fine, as you can see on the extreme left image. But if you look at the subsequent frames, which is the middle and the last image, the face has moved, but the localizer has not updated itself because the localizer is slow. So facial landmark doesn't work. Another idea is to use optical flow algorithms, state-of-the-art optical flow algorithms. They work excellently well on RGB images. But when we apply such algorithms on thermal images, they do not work. This is because thermal images inherently are very noisy, and the brightness consistency assumption, which is required by optical flow, no longer holds true. So what do we do in such cases? We ended up using a very classical algorithm for tracking the nostril, which is known as discriminative correlation filter. So this filter requires the user to input the region of interest, which is the nostril, as its initial frame, and it simply performs correlation in frequency domain over subsequent frames to keep track of the nostril or the region of interest. Now, not only that, this filter comes with a spatial reliability, which means that it constructs a probability map of where that nostril could be in subsequent frames. So if you look at another GIF, here there's a lot of vigorous movement involved in this participant's data set for this particular participant, and the tracker never fails to track the nostril. Now all we need to do is extract that intensity change around the region of interest, and we have the respiration rate. Once we have the respiration rate, we use a temporal convolution network and a two-step modeling approach to get the energy expenditure. So first, from the respiration rate, we get the volume of exhaled air. And once we have the volume of exhaled air, we use another model, which is the same model, to estimate volume of oxygen. This two-step approach is inspired by how an indirect calorimeter works, because the indirect calorimeter senses volumes first and then extracts out the oxygen. So in the user study, we had a good representation across gender and age, and there are two types of activities which the participants perform. One is cycling and another is running. So if you look at the result, if you compare the estimates of smartwatch calorie burn with the indirect calorimeter, we see that the mean absolute percentage error is 37.6%. This is similar to what prior studies mentioned, which is about 40%. But if we compare the respiration signal from the thermal camera, our error drastically reduces to 5.8%. Now, not only that, commercial smartwatches do a very poor job on estimating energy expenditure for people who are overweight. And these are the same people who will actually rely on smartwatches to reduce their weight. But JoulesEye performs equally well for both participants with normal body mass index and abnormal body mass index, or those who are overweight. So now we also integrated JoulesEye, or the thermal camera, into a smartwatch. Now smartwatch requires us to use a low resolution thermal camera, which is only 24 pixels in the middle. I'm pointing to the middle row. So here, if we use a low resolution thermal camera, our error goes up to 15.4% from the 5.4% error. Sorry. Okay, so I was in this slide. So if we basically if we reduce the resolution, the error increases. But then smartwatch can also give us heart rate information. So now if we use the multimodal information, both heart rate and respiration rate, our errors comes down to 10.1%. Irrespective, all these three numbers are still less than the 37% error which smartwatches gives us. So in summary, we have shown that respiration rate is a better predictor for energy expenditure compared to heart rate, and also conventional fitness trackers may not perform as good as JoulesEye for people who have abnormal BMI. With that, I'll end my presentation and I'm open to questions. Thank you.
Questions?
Hello, thank you for the nice presentation. I was wondering, does the system also work when the participants breathe in through the nose but then breathe out through the mouth? Or does it only work when you breathe out through the nose?
Yeah, that's a good question. For this study, we specifically asked participants to not breathe from the mouth. But I understand your concern that while exercising, it's very easy for someone to open the mouth and do a deep breath. But in our data set, we have found out that it's quite difficult to see the heat that is coming out from the mouth. But somehow it's still possible for some of the participants, but not for all. But for this study, we did not analyze it.
Thank you.
A second question?
Thanks for a great talk. I just had a clarifying question. You say respiration rate, but are you focused on the rate or the volume of air intake?
Yeah, so we first sense, so the thermal camera, the signal from the thermal camera, we get a 1D signal of intensity change. So it's a 1D signal. From that, we extract out the respiration rate, and that respiration rate is used as an input to the model to estimate the volume.
Okay, I think no more questions. Okay, a quick one, okay? So we are running out of time.
Great presentation. I just want to ask, your scenario, the mobile phone is fixed. Is it okay when you are working and holding the phone and take picture of yourself and is this time the face is moving and the mobile phone is moving, is this works?
Yeah, that's a good question. So we have extensively analyzed. So first of all, in our user study, it is necessary to like fix the smartphone in the handrail or just keep it on the desk. Yes, the mobile phone will still move, and the person is also moving, but that is why we use the discriminative correlation filter to, you know, kind of get rid of the noise which is introduced by the movement of the bicycle or the movement of the person. And we are all only interested in the respiration rate. So that filter takes care of the noise which is introduced by those movements.
Okay, thank you.
Yeah.
Okay, let's share some clips with the presenter.